Are you ready? Should we get started? Right. Okay. Since we have video recording, so I think we can get started now. Okay. First, I want to continue the unfinished lecture last week. We are talking about Dr. Zheng Qitong's paper. So, okay, basically, we know what he is going to do. He wants to figure out whether the image has a fraction and where is the fraction. Right? So this is okay. So why is they want to do it? Because in 2017, there are many CN-based image classification algorithms. They show very good results, and for the ISL-VRC challenge, CN outperforms human. So they want to know if they apply the same method on medical images, whether they can generate a very good results. So they started their research from 2017, and the image they used are the X-ray image from Chang'an Memorial Hospital. Okay. So let's take a look first of their data sets. They need, because what they want to classify is also the size of data sets for the frontal pelvic X-ray image. They only have 3,600, but they are not sufficient. So how do they do? They collect the images from the same type, X-ray images, from other human body parts. Most of them are limb. So from the limb image, they can know whether there is a fraction, and they can label. They use the limb image to train their models from scratch, and then fine-tune the model using their frontal pelvic images. Their images are of the raw resolution of 2,002 square. So, however, for a neural network can be viewed as a function, so they need a uniform input. They resize all of those images into the resolution of 215 square so that they can have a uniform input, and use those images to train a network to predict whether there is a fraction. Okay. So the format of their images are 8-bit. It means 250 grayscale. And finally, they need a set of test images. So their test image is there are only 100 images. What's the difference from their training image and the test image? Time. All of the test images are collected in 2007, and their training images are collected from 2008 to 2016. So there's a significant difference between the two sets. Okay? And they manually remove some bad images, including dark, ill positioned, and noisy images. Alright, so you know this better than me, I guess. Alright, so this is the illustration for the pelvic part. And there are, two types of fractures. One is the femoral neck fraction. It means it happens in here. And then there's another fraction called trochanteric fraction. It means it happens somewhere here. So this is the statistics of their data set. There are totally 3,300 images. Some of them are with the hip fraction. So the number is here, and some of them there is no hip fraction. The number is here. Okay, so however, this is just text look. Approximately they are 60%, half. Okay, so this is we can claim this is a well balanced training set. Okay, so let's talk about the technical detail. In 2007, what is the state-of-the-art image classification algorithm? Okay, it is the DenseNet. So this is the architecture for DenseNet. First, let me take a look. It was published in 2016, August, as an archive paper. And in 2017, CPR, it got the best paper award. So as you can see, there are many algorithms competing for the best paper award. And CPR is the most important conference for innovation. So you can see DenseNet in that year, it is a highly influential and impactful paper. So from this figure, what can we see? It shows the basic architecture for DenseNet. So let's replace it. So this is a layer. From a layer to another layer, so what do they pass information? Yeah, they pass the convolutional result. And from this second layer to the third layer, so what do they pass? So the important, interesting thing is they get signals from its previous layer, but they also get signals from their grandfather layer. So this is why it's called DenseNet, which means in this dense block, okay, so there are 5 layers. The first layer passes signal not only to its following layer, but its next layer and the next layer. And so you can see there are many lines from the first channel to the all following channels. Okay, so if they draw this DenseNet in their architecture, it will something like this. Given an input image, through a convolutional neural network, they get the feature maps. And in this block, they will pass the signal from one layer to all following layers. So that's a major difference from of DenseNet from ResNet. So okay, when we use ResNet, is there a path from its layer to its next 2 layers? No, there's not. In the ResNet, the signal only passes from one layer to only the next layer. Okay, so as you can, this is the major improvement of DenseNet over ResNet. That's what is the advantage of using this architecture. They can use less parameters and pass more information from layer to layer. So let's see the comparison first. There are many configurations for the ResNet. There are 34 layers, 450 layers, 100 and 152. The more layers, the more parameters, right? Okay. And so compared with DenseNet, yes, DenseNet, because let's see, this is a layer. So between one layer to layer, this is a dense block, and there are also many configurations. Compared with 121 layers or 169 layers, even there are more layers. Let's say 151 compared to 101. There are low layers. Take a look of this axis. It means the number of parameters. So in this dense network, it only uses say 0.9. The scale is around 10 million. Okay, so this is around 9 million parameters, but it uses around 43 million, so it can use less million parameters. And this is the first metric measured in parameters. Another metric measured in how many computational resources is the rig. Flux means how many floating points you need to use. So the scale is around 100 million. As from the two curves, you can see for different DenseNet configurations, DenseNet still use less computational resources than ResNet. So this is, you can generate so for the y-axis, it is a validation error. So the lower the better. So it means you can use less parameters and less computational resources, but you can generate the same accuracy. So that's why DenseNet got the CPR 17 Best Paper Award. And let's take a look of this DenseNet architecture. So this is different configuration. From the input image, this is the first convolution, and upsampling, downsampling, this is the pooling. And from the first DenseNet block, so within a DenseNet block, there are 6 1-by-1 convolution and 3-by-3 convolution, a pair. So there are 12 layers here, 1, 12, 24, and 48 plus 32. Okay, and finally there is a classification layer and some transition layer. So the total number will be 121. That's the reason why Dr. Chen used the DenseNet as their backbone architecture, because it is the state of the art in 2017. Okay, so they have the architecture, so they first need to train it from scratch. So they first use the LIMB dataset. There are around 25,000 images to train the DenseNet, and 90% as the training set, 10% as the validation set, because they need to tune some parameters, hyperparameters. And this is their setting. And so, okay, but however, even though there are 25,000 images, they are still not enough, because as you can see, if they want to, they use the DenseNet 121, it is the smallest architecture in the DenseNet configuration. There are still 9 million parameters. So to tune the 9 million parameters, they need some augmentation skills to enlarge their training set. So how do they do? So this is the for their fabric dataset, because there are only 3,600. So they augment the dataset by ruining 10%, and horizontal flip, vertical flip, and rotational of 10 degrees. So they can enlarge the dataset from around 3.6,000 to around, I think, 16 times at least, because as you can see, this is twice, so there will be 4 times, 8 times, and by the latest augmentation, so it can enlarge the dataset to 60 times. Okay, so this is their equipment. It's quite I should say, in 2017, okay, it is I should say, is available devices in that year. Okay, so let's take a look. This is the training progressive. In the first 23 epochs, there are a lot of vibration. Okay, and after the first 23 epochs, the network gradually converged and reached the plateau. So this is the accuracy and this is the loss. So as you can see, no matter the training loss or the validation loss, all of them are gradually decreased. Okay, so as I said, so this is the 16 times. So I should say they didn't specifically mention how many images are there public training set. So this is a number I estimate because they use 4 types of different augmentation. So I assume they have around 60,000 public images. Okay, if they use 80% because they claim they use 80% as their training set. So there are around 46,000 images, and the epoch. So there are a lot of epochs. The epochs means they use all of the 46,000 images to train their network once, and if they run all of the 46,000 images over, then they will repeat the training process again, and in each iteration they will randomly use 8 unused images. So this is the patch normalization. This is actually quite a standard approach for training networks. Okay, so this is their result. The black line here is the result generated by their network, because they only have one class. What class? The class where their layer is a fraction on the image. So they can create another. So what? This is a binary classification problem. One for yes, another for no. So basically, you can treat it as 2 classes. Because this is 2 classes, so they can draw the ROC curve. Like I said, one is the force positive ratio or fraction, and another is true positive fraction. So the ideal case is if they can generate a curve totally from the bottom to the 1.0, it means 100% accuracy. But it's impossible because every algorithm will make some mistakes, wrongly predict the result. So this is their accurate ROC curve. And the most interesting part of this paper is compare the performance of the network with human doctors. So they asked totally 21 doctors to participate in research. They are separated into 2 groups. The first is a specificity group. It means those doctors are very familiar with the X-ray images. So there are 2 radiologists and 4 orthopedic doctors. And then another group is the primary physician group. So there are 10 surgeons and 5 emergency physicians. Okay, so they use different colors to note the 2 groups. So the blue and the yellow, let's see the first group. So you can see there is a cross. The cross means the mean and the standard deviation for the first group. They are experts. So their performance is better than the neural network. And another cross is the red cross. The red cross is the result and the mean and the standard deviation for the primary physician group. So their results show their performance or their accuracy is slightly worse than the neural network. So this is to show something they want to get. Okay, yes, they use the state-of-the-art classification algorithm in 2007, and using the training process as they propose, and they show, convolutional network can generate a result as good as human physicians. Okay, so now they want to also show where is the fraction. So here we are talking. I will show you how do they generate the CAT, classification activation mapping. So this is the result of the CAT. The arrow is added by them, but please imagine, given an image like this, how do you highlight the area where the fraction is? For physician doctor, of course, they will pay attention to certain areas. But how do they do it in a neural network? Okay. So they use the method. They claim they use the method. It's called GradCAN. And the GradCAN was a paper published in ICCV 17. But however, so now I will explain the technical detail of the GradCAN. So let's take a look of the image taken from the ICCV 17 paper. So what is GradCAN? GradCAN, it is a class activation. So what does it mean, class activation? It means if you train image classification neural network, so you want to predict what the class is in the image. So here is an example. Because they train their network in the ImageNet, so there are 1,000 classes. And of course, there are classes of cat and dog. So what they want is, they want if their algorithm can show them where the cat is. So as you can see, this is cat. And where the dog is, so this is the dog. Alright, so if they can show or highlight this region, then they can combine their algorithm with some existing network visualization algorithm. For example, this is a guided propagation. So they combine their algorithm with the guided propagation. They can get this is the result. It means they will only highlight the cat. So what's the problem of this guided propagation algorithm? It highlights not only the cat, but only the dog. Okay. And they can also, for example, this is the result of, because this is, I should say, GradCAN is the generalized idea. It can be applied to many different kinds of classification algorithms. So they can also apply it to ResNet. So this is the result of ResNet, and this is the result for VGG. Okay. So let's explain. Before GradCAN, there is an existing method just called CAN. It also is used to show the highlight region of imitation. So these two figures are cropped from the paper of CAN. And as you can see, if they want to highlight the Russian teeth, then it already showed the heat map or the key points of the class Russian teeth. So if they want to highlight the cutting tree, so it will also show this is the important areas the network see and use these regions to classify whether it is a cutting tree class. Okay. And take a look here. CAN was published in CGU 17, and the GradCAN was published in ICCV 17. So it is a gap for 1.5 years. So if we need to know what is green can, we need to know what can is, because it was the earlier method, and green can is a modification of can. So let's take a look at can at first. So what is can? Can means, suppose you have a classification network like this. It means given an input image, you will have several convolutional neural layers. From the input image, you will generate some feature maps here if you have the final layer. The layer will do global average pooling to generate some one-dimensional feature maps and linearly combine with that to generate the final logit. Okay, if you have this structure, then when you do the global maximum global average pooling, you will get several values. What is the value? That is the average of all values in a single channel. So if you have those values, you will then just use the final multi-layer perceptron layer, fully connected layer to generate the login. But however, this is the key. If you have these final layers, but if you do not only sum them up, if you show them, then you will get a result like this. So for this layer is this layer, and the second layer is this layer, and the third layer or the final layer is this. So if you just use this layer, not only compute the average, but directly show them out and use the weight. This is the weight. The weight is the parameters you train the overall network. It means the network know how important the average of this layer will be. So if you use this weight and just simply multiply them on each map, then you generate the classification activation map. So this is quite a simple and straightforward approach to generate the map like this. But the key point is you need a layer at the end of the architecture look like you need a global average pooling layer at the end. Otherwise, you cannot do the can. You cannot generate the can map. So from there, okay. So for some image classification algorithm, for example, GoogleNet, VGGNet, AlexNet, for the three networks, they don't have the global average pooling layer. So what should I do? So their approach is, I should say, in the CPR 16 paper, Zhu's approach is very straightforward because they don't have the global average pooling layer. Just insert it. So they insert the global average pooling layers at the end of VGG, so they get this VGGNet-GAP. But because this is a newly added layer, it doesn't matter. So of course they can retrain the overall VGGNet gap architecture. But as you can see, the original VGGNet, the top 1 error is only 31. After changing the architecture, the top 1 validation error increased. What does it mean? Poorer performance. All right, and the top 5 is also again for VGG is also 11%, but for the modified architecture, it becomes 12%. So it means this is a sacrifice. They sacrifice the performance to generate the capability to show the heat map. So this is the trade-off. But however, for these images, you can see, okay, if they want to know where is the threshold, yes. No matter they use the modified Google method or modified VGG method, modified AlexNet, yeah, they can show, yeah, the performance of the can is quite good. And if they try another image, this looks like the mushroom, yes, they can show, yes. Okay, so it means if you prefer, you can modify your architecture to add the global average pudding layer so that you can generate the heat map. Okay, it helps you understand whether your network is correctly pay attention to certain area. All right, so okay, so where is the global average pudding come from? It comes from another paper called Network in Network. And here, this is the network in network. So in the Network in Network paper, it was published in 2014, slightly earlier. So there are two key points in the Network in Network paper. The first is global average pudding. So what does it mean? This is the architecture they proposed in 2014. So as you can see, if you use, for example, the earlier implementation of network, no matter AlexNet or the LANet, the last is the three layers. What are they? Fully connected. Okay, but they replace the fully connected layer with the global average pudding layer, and they found, yeah, their performance become better. Okay. So this is their first improvement. And then their second improvement is they added many one by one convolution layer. So that is the one by one convolution layer. In between, after the convolutional layer, they added several one by one convolution layer. But what is the one by one convolution means? It means the weighted average of many channels. So why do they want to do the one by one convolution? Because they found, first, if you want to do the one by one convolution layer, you don't need a lot of parameters. For this example, you only need 192 parameters. You can reduce the channel of the layers of 192 channels into a single channel. So what does it mean? It means you only need a few parameters. You can increase the nonlinearity of the network. So that are the 2 points of the also novelty points of the network in network layer. And the global average pudding was adapted by the CAN. And so until 1916, CAN has become an available tool to visualize networks. And even in the network in network pairs, from this image, you can see they have used the global average pudding layer to illustrate something like the CAN. Okay, but they only show the result on the CIFAR10 dataset, and they didn't show it as a heat map. So what I want to say here is, in 2014, network in network, they have shown the capability to visualize the each classes. So, but however, the experiment only conducted on the CIFAR10 dataset, so they only show classes. And in the CAN paper, CPR 2016, they show they can extend the global average pudding layer to 1,000 classes, and the result looks good. Okay. And now, okay, let's talk about the gradcan. So we see if they want to use CAN in 2016, okay, they must need a global average pudding layer, but they will sacrifice the performance. So in 2017, the gradcan was proposed. The idea is straightforward. I should answer. Okay, so what is the idea? Okay, they want to use gradient to simulate the global average pudding layer. So that is the idea. As a result, they no longer need the global average pudding layer. They can use gradient. So how do they calculate gradient? So this is the layer. As you can see from here, you have many layers. You can pick up any one if you like. For example, once they decide whether they want to calculate the gradient, okay, what do they do? Because after training the network, all parameters are fixed. Then there will be some logic before the software max layer. Software max layer is convert the logic, and here you can see this figure in our textbook in figure 5.27. Some people call it a logic, and in this figure they are called score. Meaning is the same. Okay, for every class, you will have a score or logic, and use a software max layer to convert those logics into the probability values of each class. And here, okay, this is a key point. Because all the parameters are fixed, and this is the layer. This is a layer, and there is a layer. There are several channels. They can compute the gradient from a value on a channel respected to the class's logic or class score. So okay, because they can compute this. This is just a gradient. It means if you slightly change the score here, then what will be the change happening on this pixel? So they can compute the value for every pixel. Okay, so they will get the value of the first channel, second channel, and third channel for every channel. Okay, so that is something like the global, because in the global average pudding, okay, they use the average of the channel. Okay, here the same. They can use the average of the channel. I should say, I should say, okay. Suppose let's say the value of the gradient of the pixel is this. We use this symbol. Okay, then what they do is they use global average pudding again. Okay, so this is why the method called gradcan, because this is the gradient. They use the gradient to simulate or replace the signals in the global average pudding layer, right? So they can, okay. But however, some of them are I should say, because it's a gradient. Gradient can be positive and positive. Okay. So they add a ReLU to suppress those negative gradients. And see the result of the positive value. All right. So that's why in Dr. Chan's paper, they claim they use gradient to generate the heat map. But however, after reading this paper, I found some questions. I don't know how to answer that. Okay. The first is because they use DenseNet, and let's take a look. Let's take a look at architecture of DenseNet. Okay, here you can see in the last layer of the DenseNet, there is a global average pooling already. So if so, why don't they just use this global average pooling? Because as we said, if you want to use CAN, you need a global average pooling layer. And yes, in DenseNet, there is a global average pooling layer. Why don't you just use this? And they need to use great CAN. I don't know. Okay, they didn't mention it in the paper. And the second question would be, if they use great CAN, then which layer do they pick to use great CAN? Because you see, this is the DenseNet architecture. There are many layers. There are totally 121 layers. Which layer do they use to generate images like this? Nobody knows because they didn't mention it in the paper. So there are some questions I cannot answer from their paper. And okay, yeah, okay. And something interesting is, because Dr. Chen delivered his presentation to us in this semester. So according to experience, the most tedious and job in this research is he need to label those X-ray images by himself. As you can see, how many images do they have? This yeah. For the limb dataset, there are 25,000 images, and some of them are not labels. So he need to label them. So that's the most difficult part or tedious part of this research. Okay. All right, so this is the end of our image classification course, and I'm going to talk about the image generation today, okay? Because several weeks ago, Shenbo told me he is interested in this paper, okay? It's called MedCan. So I think it's good. If we talk about the image generation, then it is good to talk about this paper. But however, if I want to talk about this paper, DDPN, I need to talk about because some things to help you understand the developing process for this. So okay, so this is the look of our topic today. MedCan, let's take a look here. It was published in 2024 this year. Okay, but however, its archive paper was released in May 23, so last year, right? So if we want to know the technical details about the MedCan, we need to starting from here. Okay, all right, because there are some, for example, also the same author, they published the 3D DDPN 2 years ago, and where the 3D DDPN come from? It comes from the improved DDPN, and where is the improved DDPN come from? It comes from DDPN. Okay, so this is the approach. And but however, as you can see, they compare the many GAN algorithms in their paper. So that's over here. Yeah. So here you can see this is the result of MED DDPN, but they compare the result with disco GAN, pixel to pixel, and the style GAN, and this is the 3D alpha W GAN, H GAN, and this is a latent diffusion model. So this is another diffusion model. And let's go back here. So just remember, this is pixel to pixel, and this is a style GAN. And take a look of our chart today. Yeah. the image-to-image translation is the pixel-to-pixel method. And the style GAN is this. There are 1, 2, 3 different versions of style GAN. So but however, the pixel-to-pixel and the style GAN, all of them were developed for 2D images rather than 3D. And here, when we read the method DDPN, they are all converted to 3D. What does it mean? They use a similar architecture, but retrain it from scratch using the 3D data. Okay, so let's start first. What is GAN? GAN stands for Generative Adversarial Network. So why do it is generative? It's generative. There is a generator. The generator can receive a latent code, or you can just imagine a noise. From the noise, it will generate an image or some signal. And they generate something, but of course sometimes they are very, very poor results. So they need a discriminator. The discriminator can tell whether it is a generated image or it's a true image. So it will tell us which is a real or fake. Okay, if the generator can generate a very, very good result, so that the discriminator cannot tell this is the generated or fake image, then okay, that is excellent. Then we will use the generator to generate what we want. So that is the method DDPN they want to do. Oh no, I should say this is a generator generative model they want to do, and this is called adversarial because if you want to reach this step, the generator and the discriminator, they are adversarial. The generator want to generate an image as best as possible, and the discriminator want to become the best detector as possible. Okay, so both of them try to improve themselves. So this is adversarial. So there are 3 different types of the GANs. The first is a regular GAN. It means they generate signals or images from the random noise. That's all. No. And the second is the conditional GAN. It means the generator generate the image not only from a random signal, but also from something condition factor. And we will see the condition factor in our following slides. Okay. So the third is the info GAN. It means the discriminator not only tell us whether it is a real or fake image, it will also tell us what classes or what is the conditioning factor of the generated signal or images. Okay, let me show some examples. And when we go back to here, it will be easier to understand. Okay, so let's talk about slightly about the development history of GAN. In the beginning, GAN was invented in 2016. So in the beginning, there are a few GAN papers, and soon it get attention very, very quickly from 2016. And from 2017, as you can see, there are only around 45 papers, suddenly increased to 200 papers. And then in 2018, it increased to more than 500 papers. So in the beginning, there is a GitHub want to collect all published GAN papers. And soon he found it is impossible because there are too many papers. So this is a stopped GitHub website. All right, so this is the first important GAN. I should say this is the first GAN to generate high resolution images. But let's take a break for 10 minutes. Okay, so let's get started. So this is the first GAN which can generate high resolution images. So why can it generate high resolution? Because it uses the deconvolution neural network. So what is deconvolution neural network? It was the paper published in ITC 15. So what it means? So let's take out the deconvolution neural network. It was designed for semantic image segmentation. It means given an input image, he wants to know which pixels belong to the object and which is not. So how do it do? It means given an input image, they will generate convolution into several layers, and then finally generate the one-dimensional signal. And from the one-dimensional signal, it will gradually enlarge its resolution to generate the final segmentation map. So here, there are many downsampling using the maximum pooling. And if they use the upsampling, what does it mean upsampling? At the maximum, given a pixel, it will be the 1 pixel of 4 pixels. And then use another neural network to reconstruct the pixels to its surrounding pixels. So there are several upsampling layers. So they can generate a map from a single 1x1 dimensional signal. And let's see how it works. For example, this is a bicycle image. And from the bicycle images, they can, so as you can see, they can generate a 1x1 dimensional signal. And when they upsample it to 14x14, it should look like this one. And this is unpooling. After the unpooling, they will deconvolution. It just means apply another convolution kernel, so they will get the result this one. And unpooling again, and deconvolution again, and finally they will generate a result like this. So the purpose of this map is to indicate what is the segmentation of the bicycle. So the paper have the second part, the deconvolution network, and the DC can just use the second part. It adopts the deconvolution network so that from an input random signal or a latent code, there is a deconvolution upsampling step, and the deconvolution so it will generate high resolution images. So from this 1x1 signals, they can generate a result as a 64x64 image. So what type of this GAN is? It is a regular GAN. There is no any condition. If they learn the network, and for given any signal, they will generate an output images. So this is the example from the result of DC GAN. And this is the LSUM dataset. LSUM stands for Large Scale Scene Understanding. And there are several subsets. For example, this is bedroom, and there are some subsets, for example, cars or birds, etc. And let's take a look here. Once DC GAN was published, 1 year later, the pixel-to-pixel or image-to-image translation GAN was also published. So the idea of image-to-image translation was, given an input image like this, they train a network. When they see this image, they will generate an output image like this one. And from this is aerial image to map. They see this image as an input. They will generate this image up. So that's why it is called image-to-image translation. Given an input image, it will generate an output image. So given input, generate output. So this is why this is called conditional GAN, because here this input image is the conditional factor. Take a look at this. Here they need not only the input image, but also a random noise. So it will generate an output image combining the conditional factor, the input image, and a random noise. So here you see from this image they generate this output image. If we fix this conditional factor and use another random variable, so we will generate another output image. So how do they do it? Again, they need paired training images. What does it mean? So in their training process, they need the training image X, and they also need a paired expected output image Y. In the training phase, their discriminator will receive not only the generated image, but also the input, the conditional factor X. So that is the illustration here. The discriminator will not only see the conditional factor, but also see the generated image to tell whether it is a real or fake image. Okay. So in this case, there is a discriminator D and a generator G. There is a first gain for the conditional factor. So the discriminator will generate a probability whether this is a fake or true image. If this is a true, I say real image, then the discriminator will generate a high probability. Will close to 1. If it is a fake image, means the image is generated, then the discriminator will generate a value as 0. So the 1 minus 0 will become 1. So this will be the loss. It means if the discriminator cannot tell whether it is a fake or real image pair well, then the gain will become larger. So they try to minimize the gain as much as possible. Here, the novelty point is they add another loss for L1 loss. It means the generated image should be similar to its training pairs Y. So why it is do they need is because in their experiment they found if suppose this is a ground truth image and this is an input image, if they only use the adversarial gain, the adversarial loss, this is their result. So let's take a close look of this result. What is the problem of this image? It is still a string thing. Okay, so I should say maybe the result is slightly unstable because you can see there are a lot of yes, it is string thing, but it is not the string thing we expect. It is something different from the ground truth image. That's the result. They add the L1 node as another penalty. They will their gain will not minimize the adversarial loss, but also need to minimize the L1 nodes. So they add a hyperparameter lambda to balance the two losses. Okay, so there will be another question. If we just set a very large lambda, what does it mean? It means let's ignore the adversarial gain and just pay attention to the L1 node. What will be the result? Like this one. Yes, something look like the ground truth in terms of the L1 loss. So we can still see the sky, see the the ground, but the detail was missing. What the detail? You see, if there, okay, the paint on the road disappears, and the detail on the trees also disappears. So that's the reason why they need the GAN, because the advantage of GAN is it can try to preserve the details. Details in what? In the distribution of the ground truth. So that's the reason they combine the two losses and generate their results. Okay, the same thing of image to image translation is the title of the paper, and the team of Berkeley, they released the software on our program on GitHub, and the name of so they call it pix to pix. Okay. So that's the reason why we will see the 3D pix to pix in our latest in the following slide. The same team from Berkeley, just a few months later, they released the cycle GAN. So cycle GAN, what does it mean? It means from an input image, they can convert into another image. So you will see, oh, this looks very similar to the image-to-image translation. So what's the difference? The difference, they no longer need the paired training data. So that's a took. They need an input image like this, so they can generate an output ground truth like this. And when they train the network, they need the paired training image. But here in cycle GAN, they no longer need the training image. They can give an image and translate it into another domain, and then translate that back. So, okay, so major difference is here. In the originally, they need the training pair, the Xi and the Yi. All of them are paired, so that they can track the network. Here, no. You can just give them two sets of images. Each set has a similar style. Okay. So they are unpaired. And how do they do? Just train two GANs. So one generator will translate the images from the X domain to the Y domain. And another generator F will translate the image from Y domain to X domain. And there are two discriminators, dx and dy. So how do they control their loss? They control their loss in this way. If an image from the domain X translated to the domain Y and translate it back to the domain X, then the X hat and the X should be similar to each other. So this is why they call it the cycle GAN. Go here and go back. Okay. So if an ideal case, the discriminator dx and discriminator dy works well, they can tell whether it is a generated or fake images. And the generator G and the generator F works well, they can successfully translate images from one domain to another domain. Then, okay, if all of them are well trained, then we can translate the images from one domain to another domain and translate it back. So this is the result from this input image. Let's see, take a look. From this input image, they will generate translate to another domain. So this is a photo and this is a painting. And from this domain, they will translate it back. But however, you will see there are something different. For example, the color of the flower here is red, but the color of the flower here become yellow. So what is it? That is the loss in this term. Okay, loss is this term. So ideally, the network should minimize the loss, But of course, it is not so easy to do. So they will always generate some difference from the input image X and the reconstruct image X hat. So let's take a look at this example again. As you can see, the color of the grass is red, but the color of the grass is become brown. So, however, the ideal case is every generator and every discriminator works very well. Okay. So, they show using this method, they can translate the input image into not only one domain. So this is input, this is a photo, and this is Monet's style, Van Gogh's style, Cezanne's bread style, and ukiyo-e style. Okay, how do they train multiple generators, so they can translate a single image into multiple image domains. But however, there are of course some failure cases. This is input apple, this is output orange, but it doesn't work very well, and it makes some mistakes. This is a dog to cat, but however, the result is still look like a dog rather than a cat. And this is Putin's picture. They want to translate the horse to zebra, but it cannot tell there is a person on top of the horse. It also translated into the zebra. Okay, so that's the limit of the cycle gain. So here, let's make a brief summary. DC gain, okay, it is the first gain to generate the high resolution images. And the image translation is, okay, this is a conditional gain rather than a regular gain. We can use the compare the training images to our image we want. And the cycle gains means we no longer need the paired training images. So there is a few questions. Now, if you can generate some very nice looking images, how do you measure it? What is a good metric to measure your generated image? And the second question would be, how do you use a single, here, let's take a look. If you want to generate 4 different styles, you need 4 different generators, because every generator can only translate image from one domain to another domain. But how can you train a single generator so that you can translate or generate images from 4 domains? Okay. So the first question was addressed by the metric FID and the precision and the recall. And the second question is addressed by style gain. And let's take a look of their release date. Okay, so this is FID. FID was released after the cycle gain. And this is the style gain. Style gain 1, 2, 3, not including the 0. 0 means a progressive gain, right? So this is another, I should say, approach. Okay, so let's go back here. So, okay, let's talk about the FID. FID is the franchise inception distance. The concept is, let me explain the concept. Now, you have a generator. You can generate a lot of images. So, how do you know, oh, the result of the generated image are similar or dissimilar to my original set of images? Okay, let's take a look here. Okay, so suppose this is the original image, horse. And this is generated image, horse. Is this picture similar to this one? So this is just a pair of images. If you have 10,000 images of horses and 10,000 images of generated horses, then how do you measure that? the similarity between the two sets of images. So the FID means, okay, we can do it in this way. First, given the image, we use a pre-trained inception V3 on ImageNet. What does it mean? Inception V3 is the Google Net. It is an image classification task. So, given the image, how do they know whether the image belongs to which class? Okay, so from layer to layer, finally they will generate the probability of the 1000 classes. But before it, there is a final layer of it is a vector. It means the vector presents the image. So given an image, you can use any pre-trained image classification network to get the image print descriptor as a vector. So they use Inception V3 GoogleNet. Therefore, they can convert an image to a vector. So if you have 10,000 images, you can generate 10,000 feature vectors. In the vector space, okay, you assume their distribution are Gaussian. So you can just measure the two Gaussian distribution by the distance of their means and their scattering condition, scattering status. So suppose there are two Gaussians with mean m, w, and n, and their covariance matrix CW and C. This is the FID definition. For illustration, it looks like that. Given an image and use a convolutional network to get the feature. Okay? What is the feature? The feature before the softmax layer. Okay? So this is a feature, and many images will have many features in the space. And there's another clusters of features. Okay. One is real and another is generated. Then FID just measures the distance between the centers of the two clusters and how much they overlapped. Then let's see some capability of FID. So this is clear image, and if they add some noise, okay, because you can control the level of the noise, and from a lot of images you add a lot of noise, so you can generate a different layer. Then they measure the FID. So the ideal case, the two sets of images are totally set because there's no noise. Then the FID value is 0. And with the increased noise, the FID value gradually increase. And this is second distortion. This means blur. And the third distortion, it means you distort the image using the squirrel rotation. And this is a pepper and salt distortion. And this means you randomly crop out some regions from your original image. So what does it mean? It means FID certainly represents the distortion of the original set of image and the altered image. So from this figure, they want to show FID is effective. Okay. And all right, so this is FID. Now, at least we have a metric to measure how similar of a group of a real image and a group of generated image. Okay, now let's talk about the style gain. The beginning, the scale gain 0, it is not called style gain, it is called progressive gain. Okay, and then there is a style gain V1, V2, V3. All of them are from NVIDIA. So, okay, this is a very amazing, impressive work for 4 years. So what is progressive gain? First, they found gain is difficult to track. It is very easy to corrupt. So how to address the problem? They proposed a method to train the gain progressively. So what does it mean? First, just train. If they want to train again, can generate images of 124 square. So this is a very high dimensional, difficult. So how to do it? Just train a very small GAN from 4x4 to 4x4. So this is relatively easy. And if the parameters are well learned, then they add a new layer 8x8 and 8x8. So it will use just the train the parameters in 4x4 to train the parameters of 8x8. So it's like a gradually fine tune. You in the beginning train the easier one, and then tune the more difficult one. And then, of course, the last layer is the most difficult one. And then here is a figure, so like this one. From the low resolution to train to high resolution. And you can take a look at this, how many days they need to train the network. So in the beginning, it's very fast, 4x4. But in the latest work, it will take a lot of several days to train it. And so how do they add the new layers? This is just an example. If they have the 16 by 16 layers, okay, they will add the new 62 by 62 layers with a hyperparameter alpha. So in the beginning, they will set the alpha as 0. What does it mean? It means the 32 by 32 layer that doesn't matter, because if the alpha is 0, okay, when they use backpropagation to tune to update the parameters in this layer, because if alpha is 0, they will not be updated, and they gradually increase the alpha from 0 to 1. What does it mean? It gradually updates the parameters in the 32 by 32 layers. So that's the reason they can gradually, so this is called progressive GAN, because they train those parameters in a progressive approach. And then when the layer of 32 by 32 is stable, then okay, they will train the next layer. They need a new data set to validate their approach. So they created the Celeb A HD data set. Celeb A, as we mentioned in our previous, is a free data set. Okay, everybody can get it. And the AV image on the Celeb A data set are the faces of celebrities. But however, because Celeb A is cropped from the internet, so their resolution is, some of them are large and some of them are small, and some of them are not square. So they need to, I should say, do data preprocessing to clean up those data sets. So how do they do? First, for example, given this image from the Celeb A in the wild data set, they need to remove the JPEG artifact. So this image is JPEG compressed, first one. Okay. Apply the JPEG artifactual removal, they get this second image. And they apply the super resolution to upscale this image, so it looks really clear. Then they do mirror. Mirror means, so you can see this is the mirrored part. And this is also a mirror part. Then apply a Gaussian filter, because this is the face is the region they want, and apply the landmark detection algorithm to detect the two eyes and the location of the mouse, and rotate it. So it will get an image. The two eyes will, all of the two eyes and then the mouse will be well aligned. So once they get the Celeb A HD dataset, okay. This is the architecture. They can generate, just apply the progressive GAN, generate the result. So this is the largest image resolution, 124 squares, and this is 212 squares, and this is the 256 squares. So impressive. The results are quite impressive, state of the art of that year. But however, that is for face. But for other data set, is this so good? No. There are a lot of artifacts. So take a look. This is LSUM. LSUM data set, we see that for DC gate. And there are another subset, for example, bicycle. So this is, you can see clear artifact here and artifact here. Something wrong. Okay, this is very, very unexplainable. What is? But however, this is a style gain, right? And okay. Oh no, that is a progressive gain. And then next year they developed the style gain. So they change. They base their previous research work, progressive gain, and developed a new style network architecture. So here you can see this is still 4 by this is progressive gain. The layer is 4 by 4, 8 by 8, and 6 by 6. The set they use 4 by 4 and 8 by 8 and 6 by 8. They use the same approach to train the network. So what is the novelty? The novelty is first, in their progressive gain, they assume the input data is just a signal following Gaussian distribution. But in style gain 1, no, they assume the Gaussian distribution may not be a good source, I should say, the distribution to model the real world images. For example, for why? Because as you can see here, pay attention to the feature of what? The length of their hairs. So this man, his hair is short. This man, his hair is also short. This woman, both of them have long hair length. Okay, so if we just want to describe the length of human hairs, does it follow Gaussian distribution? Of course, no. Gaussian distribution means there is most of the value is closer to its mean. But it's not the case for our human hairs. Most of the hairs are short. Either it is long. There is no mean that the mean value doesn't mean anything. Okay, so they propose to use latent immediate latent space. This means, so let's show this image. What is it? So if there are some feature, its distribution should look like this one. And if they want to use the Gaussian distribution to model this distribution, this will be their result. It is not well distributed. But if you use the immediate latent space, okay, how do I generate the immediate? Just use many fully connected. It is just a multi-layer perception. Okay, then they can create the immediate latent space and use the immediate latent space. Okay, they will learn the parameters in the adaptive instance normalization. What does it mean? Okay, given something, okay, the something means a constant input signal. So here, for style gain, this is their latent. But to generate the image, let's see here. Okay, in the progressive gain, they use the latent Gaussian variable to generate the 4x4 first layer. But in style gain, no, they don't need it. They just use a fixed, constant 4x4 by 120 signals. They only need to control the latent. The latent no longer is the input signal for the generator. The latent vector z will be converted into an immediate latent vector w, and the w will be used to generate the parameters for adaptive instance normalization. Okay, the adaptive normalization will influence the values in each channel after the convolutional results. So here, okay, so let me show. Once they develop this architecture, okay, then they need a new data set to validate their network. So they create another data set for FFHQ, the flicker phase HQ data set. This is very similar to this celeb A HQ. So what's the difference? The first difference is because the celeb A dataset, all of them are celebrities. So will there be baby in the dataset? No, there will be no baby in the dataset. And are there very old citizens in the dataset? No. Okay. Are there Muslims in the dataset? No, because all of them are celebrities, movie star and athlete stars. Okay, so the variety of this dataset is limited. So they need to create another data for FFHQ. They grab images from Flickr. So you can see this is the baby. This is a black, I think is a African priest or something. The very old a Muslim and some Asia with makeup on their faces. So the variety of the FFHQ data is greater than the selected HQ data set. Okay, so this is the result. Let's pay attention to this. They add a noise. Why do they add noise here? Because they found some features on all human faces. It is unable to model just using any signal. What's this? For example, hair. Because the signal hair are too random as noise. So they just use noise to generate the result of the hair. So this is a comparison. If they use no noise and generate the image, you can the hair is what? Too smooth. Okay, the same as the background. If they only use noise to the fine layers, so what is fine layer? Let's take a look of the progressive gain structure. So this is fine layer, high resolution layers. And if they use only to high resolution layers, they will generate look like this. They generate some details, but overall it's still smooth. If they generate only the coarse layer, okay, so this is fine layer, we see something. The coarse layer, we will see the result. So they add a noise to every layer, they will generate the result. Okay, here, this is a number of FID. So once FID, the metric will pose. They use the FID to measure if their baseline progress gap, the FID is the largest. And with their latent, the remove traditional input means just use a fixed constant as their input. And add a noise, they will further reduce the FID. So this is the improvement of style gain over progressive gain. They optimize the parameters. No, they modify the network architectures so to generate better results. And they also found a very interesting thing called layer mixture. So let's take a look here. Suppose this image is generated by a latent code, say here, this is a Z1. And this image is generated by another latent code, Z2. Okay, because the latent code will control the parameters in the ADA-in module. So if the Z1 generates the parameters of the ADA-in module for the course layer only, and the Z2 generates the parameters of the ADA code for the course layer. So it means for certain layer they use the result parameter generated by Z1. For certain layers they use the result generated by Z2. Then what we will see? We will see, okay, the course style from the second the B combine it together. This is generated data. So what does it mean? It means because there are many layers from 4x4 to 124 to course to 5. It means the layers control something. For 5 layer, it control for course layer. It control the position of the face. For 5 layer, it control the color of the background, the color of hair and the background. Okay, so style game, and now this is why it's called style game, because every layer is meaningful. It can control the style of the generated image. But does it happen for other datasets? No, only for face dataset. For other dataset, they didn't find such properties. Okay, because human faces are highly structured, so it is easier to model by the network. But for other datasets, for bedrock and for cars, they don't share the similar structures, so they cannot find the property in the style game. Okay, so now this is style game V2. What is V2? V2 means they found that there are some problems in the style game. It is called the droplet artifact. This means if you enlarge this image, okay, so what is this? What does this mean? And what does this mean in this image? Okay, it's very so of course once they found this, and there is another problem, the face artifact. So this is the face. The two teeth was aligned on this one, but when the face slightly rotated, the two teeth still aligned at this line, and when the rotation angle is greater, the teeth is still aligned this way. This is an artifact. So when they developed the style game V1, they know the artifact, and they solve the artifact in style game V2. And for first, why is the droplet artifact? Okay. They very quickly know, this is the case, a very severe droplet artifact. Okay. This is relatively light. Okay, they know it very quickly. It is caused by the ADA-in block, because if they disable all of the ADA-in module, then there will be no such droplet artifact. Okay, but however, as you can see, ADA-in, it is the key point for the style game V1. If you remove the ADA-in here, then it will be no longer the style game. So what do they do? Change the architecture. So this is the style game V1. They remove the ADA-in and change it to the modulation and the demodulation. So there is no longer ADA-in. However, in the modulation version, the parameter is also controlled by the immediate latent space vector W. And the second problem is what? why is there the facing an artifact, face artifact? Okay, they know it also very quickly. It is caused by the progressive training. So in the beginning, they have the progress scan, and based on the progress scan, they developed the style scan. But now they found, okay, the progress scan in the beginning, yes, it can help them to generate a very stable game, but it will have such artifact. How to solve the problem? They solve the problem in a straightforward way, no longer progressive. It means, given architecture, they no longer train the network from 4x4 to 8x8, 16x16. No. Given architecture, train it from scratch, brute forcefully. So that is Stargame V2. First, they take the data in out. Second, train the whole architecture from the scratch. Okay. So there's a comparison from their baseline style game. If they do such modification, then they will generate better results. So measured in FID. And if they measured in the path length and recall and position, they also generate a good result in terms of sign card data set. So let's talk about how is path depth. That is a metric used in measure the result. Path length means, let's take a look of this architecture. It means our Z is our input. Okay, if we slightly change the value of the input vector Z, then of course our output image will also change. So how much the output image changes? It is the path depth. The ideal case is if your game is very stable, then if you change the value of 10 to the -4, very small change, then you can measure how much it will change in the output image. So how to measure it? They just use a VGG and to measure the output space. So the smaller the path length, the better. Alright, and the latest two measures is precision and recall. So here we need to talk about the limitation of FID. So let's compare the two images. Both of them are generated, and compare with the original and mixed data set. Their FID are all 32, and this is okay. The two set of images are all generated, and their FID value is 65 and C2 compared with the original Celeb A data set. So, but their FID values are similar. Do you think their quality or the distribution are as similar as the original and mixed data set? Okay, so that's the limitation of FID. And how they propose the precision and recall to address the problem. But let's take a break now. Alright, so this is the limitation of FID. It cannot, even though the FID values are similar to each other, it's very difficult for us to tell which distribution is, more closer to the original distribution. So they propose precision and recall. The definition is simple. Precision means suppose you have two distributions. How much of the Q can be reconstructed or generated from P? So this is precision, and the recall is the reverse relation. As a result, if the two distributions are non-overlap, then the precision and the recall both of them are very low. If they are highly overlapped, then the precision and recall are high. If one is covered by another, then you will have a low distribution, a low precision, but a high recall. Okay, so use the two measure. They can they want to show that their style gain V2 generate a better. The best case is precision is high and the recall is also high. So here they show their recall is better than the style gain V1. Okay, and this is a very I should say, how do how much computational resource they used to finish the style gain V2 study? Totally 51 years. Okay, so it's very amazing because they are from NVIDIA, so they have abundant resources to do it. But soon they found another problem. It's called, they solved the problem in style gain V3. So what's the problem? Let's take a look here. It means aliasing. So let's see this example. If they, okay, you see a lot of image here. What does it mean? It means you slightly alter the input signal Z, then the style gain V3 will generate an ideal case. It means if you just take a look of this line, then the results are almost random. But if you took at this line, the result of style gain V2, okay, there's some fixed patterns. That's the problem. And if you compare the result, okay, the left one is style gain V2, but the right one is style gain V3. Okay, they slightly alter the input vector Z. Then, okay, instead of V3, the results are very smooth. But instead of V2, you see some pattern fixed here. And they found something wrong. They should not be the pattern. And if you take a look at this, okay, instead of V3, okay, you see some pattern. They call the pattern alias. So it's very clear. Some pixels are just brighter or darker than other pixels. So that's the aliasing. So they solve the problem. Yeah, in their style gain V3. How to do it? Okay. They convert the input image to Fourier domain. Okay. All right. So, however, from here they even measure the FID, and the FID become much lower than the style gain V2. So the research is very impressive. They use 4 years, so many computational resources to develop the style gain V3. Okay, very, very excellent. Okay, and because the style gain V3 is also layer by layer, so they still can generate the style mixing, just like the style gain V1. So they, okay. And now, we are talking about some diffusion model. Okay, now that's the point I want to show. But the diffusion model, the developer of the diffusion model is somehow very, I should say, complicated. And so we will just talk about the DDPN and the improved DDPN and so let's go back to the second. And our DDPN and the improved DDPN and the 3D DDPN and the matte DDPN. Okay. So what is diffusion model? Diffusion model means it is also a generative model. It means if suppose this is diffusion, the original case, and we add a noise step by step, then our original image will be altered by the noise, and gradually it becomes a mass of noise. So this is the forward pass or diffusion pass. If we can find a way from the random noise and gradually reverse the process, then we will generate something at the end similar to the input image. But they are perfect. It's not perfect, so you will see some noise here. In the IC analog 15 years, they call it a drift term. So this is just like models. Create a model so that you can create an image from a noise input. And in the 2015 paper, they have shown some application. For example, in painting, if they can model how this image, this is a trunk, become a random signal, then they crop out the central region like this one, and use the reverse signal. They can reconstruct the central region, and it still looks like the trunk input. They also apply the approaches to the emit dataset. So these digits are their generated result. But you can see, for example, this and this and this, the quality is not very stable. Okay, so although diffusion model was released, the first diffusion model was in 2015. Okay, it doesn't attract a lot of attention because at that time, GAN, it is on its road. Many new GAN's algorithm was explored and developed. Okay, the first important diffusion model for image generation is DDPN. It was published in 20 June, but it is an archive paper. The official, actually, the conference it was published was in Europe, IPS 20. The concept is identical as the ICML 15 paper, but there are some novelty and contributions. First, it is the first paper can generate high quality images, right? And it is also the first paper they show a generation model comparable against the GANs. So let's take a look of the DDPN definition. Okay, from a clear image, okay, there is a forward process. It means add a noise, and add more noise. But how to add the noise? They model it as a Gaussian distribution. It means, so the XT is the more noise image, and XT minus 1 is the slightly clear image. So they assume they will get the XT from the XT minus 1 as a Gaussian distribution. The mean is the XT minus 1 times a constant. And the covariance will be an identical matrix times another factor. Okay, so this is definition. And how about the reverse definition? The reverse definition, they also model it as a Gaussian distribution. It means now this is a reverse. You have a noisy image. And what will be the less noisy image, T minus 1? Okay, it will be also a Gaussian distribution, but the mean, you need to learn it. And the covariance also, you need to learn it. So if so, that's their setting. Let's set so here. Because there are many steps, so how many steps do they use 1,000 steps. And from each step, they need the parameter beta t. And then how do they set the parameter beta t? From 0.0001 to 0.02, linearly increase it. So it means you have 1,000 Gaussian distribution, and you can use the parameters beta 1 to beta 1,000 to control the 1,000 image Gaussian distribution. All right. So the next question is, how do they learn the mu for the reverse distribution, new reverse process. Okay, then they use a method called variational lower bound. Okay, so what does it mean? It means, okay, from this equation, it means given a random noise xt, and if they have the reverse distribution, then the distribution of not only t, but the t minus 1, t minus 2, to the final output image x0 order reconstruction can be expressed as a jointed the product of the probability. Then they use the variational lower bound to measure the probability it will less than this expectation. Okay, so there will be a lot of mathematical equation, but let's quickly go through it. So from the lower bound, so what do they get? It will be a summation of the first term and the many median term and the last term. And the first term will be a constant. And then the middle term will generate a result like this one. It means if they want to minimize the loss or the low bound, the learned means should be the term, the tilde you had. So what does it mean? It means if you can use a neural network to learn this term well, given an image, a noised image, and given the step of t, if you can learn, and any kind of noises, if you can learn it well, you can reconstruct the, well, it will be the optimized process to reconstruct the image. Okay. So that's the method how to do. They assume they can learn the, I should say, model those noise. Then they can reconstruct the image. So, okay, let's skip those mathematical. So that's, okay. So we say there is a first term, it's a constant, and there are many middle term. From the mid, and then there is a lattice term. The lattice term is this, like this. It will convert those signals from, I should say, noise, and convert it to the RGB color space. Oh, okay. So, all right, what I want to say is, they can induct the final result as, so this is epsilon means a noise, a Gaussian distribution, and this is the neural network they want to, they use the neural network to learn something from what? Given the noise, this is input clear image, and the alpha hat are coefficient from beta. So because the betas are given, we can calculate the alpha t hat. All of them are constant. Given the input clear image and the noise, we can combine them to generate a noisy image. And the step t. So it means we need to learn a neural network to predict the noise from a noisy image and its step. Okay. Once they get the mathematical expression, their training become very straightforward. They the x means their training image. Give a training image, and they generate the step t from 0 to 1000 randomly, and randomly give the Gaussian signal epsilon. Then they train their network to minimize the error between the given noise and the predicted noise. That's all. So how to predict the noise from a noise image generated by the clear image and the random noise signal, and the step T. So this is what they need to learn. If they can learn the neural network well, it means it is a very good epsilon predictor. Then in their sampling phase step, given a random noise, they reversely generate a random noise and use the predicted noise to reconstruct the random noise and plus the random noise. Okay, so that's the process. Okay, so let me skip the detail here. Okay, so because what I want to talk about is, yes, they developed a method and generate a result like this one, given a noise input, and they train the neural network, so they can step by step reconstruct the clear image or generate some images looks, and this is their final result. Okay, so what I want to talk about here is, yes, they use the method. This is not GAN, no longer GAN. This is a diffusion model-based approach. They generate a result like this one. Okay, and this is for Celeb AHQ, and this is for CFAR10. Well, compare with this image about this image. So that is the improvement. Once they define those mathematical equations and train the networks, they get very promising results. Okay, and they compare their result with GAN. Also, what we see style GAN 1 and style GAN 2. Okay, style GAN 1 and style GAN 2 compared with DDPN. Style GAN is better. So they didn't generate the state-of-the-art method, but they proposed a very normal approach. And right, so let's talk about method here. So let's take the chart again. Here they propose their DDPA, but in terms of performance, it is worse than style GAN V1 and V2. But however, this is open AI's work. They fine-tune DDPA, so they proposed the improved DDPA. Okay, so let's take a look for the improved DDPA. And okay, so what they found is here. Okay. First, they question, because we said in DDPA there are 1,000 steps, right? And then they set the beta 1 to beta 1000 is 0.1 to 0.2 linearly. They question, is this adequate? They found no, it is not. Why? Because it means in the beginning, if they use the noise schedule, they add too much noise in the beginning. So this is the DDPA. The result of DDPA is like this one. In around 200, this is 0, 100, and 200. Around the 200 steps, there are a lot of noise. So they propose the cosine noise schedule. So this is the result of DDPA, and this is the added noise of the cosine improved DDPA. So for improved DDPA, they add less noise in the beginning and gradually put the input noise almost linearly. Okay. So from this figure, what they want to show is, in DDPA's approach, if they ignore the first 20% steps, then result measured in FID are almost the same. So what does this mean? It means if they just use whole DDPA's original approach, the latest 200% are useless because of their noise. If you reconstruct those, nothing helps. So if they use their cosine noise schedule, then if you remove the first 20% reversing process, it means here, then it will be very, it will generate a very different result. So the FID value become greater than 60. So this is the, in addition to this, there are some, of course, some minor modification, but this is the most important one, right? Okay, so let's talk about the 3D TDPA. So this is our final target is the MED TDPA, but let's take a look again. 3D TDPA is the previous work of MED TDPA. It was published 1 year earlier. And let me talk about something about. So from the improved TDPA, the same two authors, Nicole and okay, let me see. A few months later, they published a new paper called Diffusion Model Bit Scales. This is a very, very important paper because from this paper, the researchers of genetic model, genetic method, they soon got a hint. Okay, see here. This is where StyleGAN v3 was released. StyleGAN v3 is very, very impressive, but it's also very complicated and difficult to train. From the paper Diffusion Models Bit Gains, they found diffusion model is a feasible way to train and can generate a very good result. So from this point, there become a lot of diffusion models papers published. And of course, including our 3D TDPA and the MED TDPA. Okay, so let's about what is the 3D TDPA. Here, they just use TDPA, almost totally the same. They didn't modify anything and apply it to NI image. So that's 3D TDPA. Okay. So, so from here you can see this is again from a clear NI image. They add a noise and step by step, and then finally they generate the almost a purely noise image. And then we want to, from the purely noise image, reverse the step by step, and generate the clear image. So the architecture is TDPA, but they use the improved TDPA because they want to use the cosine noise schedule. And to reduce the step from 1000 to 255 and change the 2D image to 3D image. That's all. That's almost all. It is easy to change from 2D image to 3D image because image for them it doesn't matter. It's just a vector in the space. Because when you see the approach, when you see the equation in the formulation in okay, TDPA, okay, this x for them is what? Just a vector. It doesn't matter it is a 3D or 2D. It's from a 2D or 3D image. Okay. So, okay. Okay, so they need training data. How do they get the training data? They get the 1,500 contrast enhanced NIT1 image from here, the National Taiwan University. Okay, so they call it the ICTS dataset, intracranial tumor segmentation dataset. Alright, fine. So let's take what is the ICTS dataset. So there are okay. This is the illustration. Because it's a segmentation dataset, you can see there are many segmentation labels. But for them, they don't use the segmentation label. They just use the image only. And this is the statistic. There are totally 1,050, and there are different types of humor. Right? Okay. Okay. Because the resolution of these NI images are very so they are the smallest one is 197 square and the largest one is 512 square. They need to resize it to 64 by 64 by 64. So for their first paper, 3D TPM, they use this. This is their first setting. Okay, and this is their generated out. They compared their 3D TPM against the two GANs, CCE GANs and 3D Alpha W GANs. So from these images, which is better? This is a real. Sorry, because I'm not a medicine specialist. Can you tell me how to read these images? Okay, so this is a problem. What's the problem? We don't have a good judgment or measure which generated the image is better. So that's why we see FID, right? FID is a approach to measure how good are your generated image. I should say how closely your generated image set to the ground truth or the original data set. So the first is FID, and the second is precision and the recall, right? Both of them are trying to measure it. But in this paper, they didn't report FID, either FID nor the precision and the recall. But however, okay, so they report this NSSIN. So let me explain what is NSSIN. Okay, so NSSIN is multi-scale structural similarity. Okay. It is a way to measure the similarity between two images on different layers. So the signal 1 and the signal 2, you just imagine there are two images. So because there are two images, you can calculate the contrast, okay, for every pixels on the two images. And you can also compute the structures for the input image, and that is become the mu and the standard deviation. So because of that, also they are great. And this is first layer, and you can downsample them to a smaller layers and compute their contrast and their structure. Okay. So you can do it layer by layer, and finally, this is the similarity between the two layers in terms of illumination and in terms of contrast, in terms of structure. Okay, so this is for single layer, and this is for multi-layer. So just to keep a concept, what is the NSSIN? It is a measure between two images, how similar they are. Okay, if the number is greater, then it means they are similar. So the index is from 0 to 1. The 1 means the two images are totally identical. The 0 means the two images are very, very dissimilar with each other. Okay, so they report this NSSIN. So let me explain what this means. Given, a set of images, they can generate a lot of images, right? They first compute the average of the set of images as a reference image. Then they compute the NSSIN between the center, the reference image, and the generated image. Okay, and then because every pair of image will generate the SSIN index, they compute the average of the all pairs. So it is somehow like a standard deviation in terms of the calculation. So what it means? the real image, the standard deviation will around 0.84, and their result is 0.82, and so which is more closer to the real distribution. Theirs. If you think, if you assume the NSSN here is just the standard distribution, so what does it mean? If we have two distribution, and I know the distribution for this and for this, the level of cluster of them are more similar to each other. Maybe, I only can say, maybe the two distributions are close to each other. So they report this number, but however, it's very, although it is very weird, the problem is they don't have a better metric to measure it. Okay, so right, so let's keep going. So they published the paper in NIDL. It's the medical deep learning, medical image deep learning conference or journal. I forgot. Okay. Maybe journal. All right. And okay, and they also do an interesting experiment. It means, suppose they have 200 images. Okay, 50 images from the real, 50 from their 3D DDPA, 50 from the first cat, and 50 from the second cat. Okay, then they ask the 3 doctors to each of them have experience of 15 years, which is real and which is generated. Okay, so their result is the 3 doctors, if they see the real image, but they only correctly predict the accuracy is 40%. And if they see the 3D DDPA, their results, they will say 60% of them are real. So what does it mean? I don't know. Okay, why? Because this is their report. I tell you, maybe that, as you said, they just cannot judge it or just didn't pay attention to it. Okay. But just like this one, okay, they also show here it is the 44, 40, the result is only 64, and this is slightly larger, 128. So, can you again? Can anybody help? how to tell which is better? Why? Sorry, I cannot see. Can you?
These 2 layers, but real cannot. It's very simple.
The test is not to show that 3D DDPA can produce the image better than real. It just support that the 3D DDPA result can fool people and make the quality similar to the real image, because the MR image will still have some artifact. So maybe I think that is this artifact make the radiologist can tell which one is generated by 3D DDPA and which one is the real image. So the result they show is just, I think it only can make a conclusion that the 3D DDPA is good enough to make people can tell the difference.
So, okay, at least it shows VDD. Okay. So, that's a look of the experiment. So this is their native DDPN. So what's the difference from native DDPN to 3D DDPN here? Okay, they insert the conditional factor. Conditional factor is what? Mask. Okay. So here, although there are many tumors or segmentation regions here, they didn't use it. Okay, and in their second paper, they use the segmentation, so say, region as the conditional factor. So from here, the major difference is their input data is become different. So how basically the network almost the same, but currently they need to predict the error. Okay, let's go back here again. Here, as we say, given an input image, a noise input image, and a step, the network need to predict what? Predict the epsilon, the noise, so that they can use the predict epsilon and the noisy image at a step t to reconstruct the previous step. And here, what they modify is they use the conditional factor. So they need to predict the, I should say, use the, they combine all image with their conditioning factor to predict the epsilon, the noise, so that they can generate their previous step. So that's all. That's a modification. So how do they do? Okay, they use segmentation data here. So why do they want to do it? That's it. Let me explain. Because if they can generate images with tumor, synthesize the tumor region, and because they have the mask segmentation information already, so it means they have very, very good labeled training data. So they want to combine the labeled training data with the real data to train a segmentation tool, a segmentation neural network. If they show the segmentation network can perform better than segmentation method trained using by real data, then that's a value. It means their synthesized image can help generate better segmentation tool. So they use another data set called NTUH data set. So let's talk. What's the difference between the NTUH data set and the ICTS data set? First, there are more images. There are 1,000 and take a look. So this is 1688, and this is 1015. So this is just slightly more 100 images, and there are more I should say type of tumors, and I found something very interesting. There are 6 authors of the ICTS dataset, and there are 9 authors of the NTUH dataset, and 5 of them are overlapping. Okay, so what's the difference of the? Okay, they say the paper of the ICTS dataset focus on how they compile the dataset, and the NTUH dataset, this is another paper. They focused on using several existing segmentation tools to test their the data set. So although the two data sets are slightly different, but highly overlapped, I think. Okay, the next issues. How do they combine the segmentation conditional factor into their image? So they use a channel-wise concatenation. It means this is image. They treat it as a first channel. And for the head and the tumor channel, they treat it then as the second and the third channel. So if you see here again, here you see a cubic. In fact, it's not. Okay, this is just an illustration. It means given segmentation label, it will convert into this tensor, and this is a one-hot encoding method. For 1, it only can be 1 or 0. If it is 1, then it means this is a head area. And for the third channel, if it is 1, it means a tumor. So they can, from the training data, because every training images have a ground truth segmentation table. All right, and then apply the same algorithm. Almost the same as the DDPN or the 3D DDPN. The only difference is here. They use the L1 loss. And let's see the DDPN. DDPN, in the DDPN, okay, they use the L2 loss. This is the only difference. Okay, and why they apply the L2, replace the L2 norm with the L1 norm, they say the result is better. But they didn't show the result of L2 norm. So we don't know. We just know, okay, they finally used the L1 norm. All right? Okay, so this is their generated real. So this is real, and they made a DDPN. Okay, so here, you see the 3D pixel by pixel. And we know what is pixel by pixel. It means you need to pair the training data. Okay, so this is the result. And it means they must have some source, but I don't know what the source is. And this is a style gate, 3D style gate. So as we see, we know the structure of a style gate. So it converted to 3D. All right. And this is LDM, means latent diffusion model. Okay. In fact, latent diffusion is a very, very important paper. Now we use the stable diffusion and many methods like DALI-3, etc. It is from the stable. Okay, so let's take a look of this. So this is a latent diffusion, this one. Okay, and there are many generations, and it currently, I should say, it is the most popular diffusion model used. And why latent diffusion model is important? Because it can create a very high resolution image. Okay. But we want to talk about here now. We just keep in mind. Okay, yeah. Okay, here. This is a latent diffusion model. All right. Okay. First, this is a result they show, but they didn't generate any tumor in the image. So this is something like the 3D DDPN, and this is the result of the generated tumor. To generate tumor, they can only compare their result with 2 existing methods. This is pixel to pix, 3D pixel and the 3D disco game. And they saw from the pixel, there are artifacts. They claim a tumor should not look like this. And all right, and because those tumors are generated, so they can use their input conditional factor. They can control the location and the size of the tumors. And of course, the other 2 GAN-based algorithm can also generate a result like this one. So which is better? Okay, I don't know. they only show the result, but there is no way to measure them numerically. Okay, and this is okay because all of them are generated. It means given the same fixed condition, use different random variable z, they can generate different output images. So this is sample 1, sample 2, sample 3, and okay, sample 10. And okay, so yeah, this is their key point. So let's see the configuration. If they use 1,000 real image and 1,000 synthesized image to train a UNet, 3D UNet, and okay, because here you can see there are split dataset, training and test. Okay, from those test set, what is the performance of the trained 3D UNet? Okay, so this is the first setting. If only real image used is best. But however, if they increase, in this case, all of the three results are trained by synthesized dataset. And then in this, okay, they modified the setting for the three, they train the 3D UNet using 100 real, 1,000 real and 1,000 synthetic. And in this figure, they add more synthetic images. Then compare with this, the red numbers means the best result. So with 2,000 synthesized image, the trained 3D UNet generated the best result. So this is what they claim. So this is a profit using the okay, here they show some numerical comparison. Okay, so FID, what do we know? So they didn't generate the best FID. Instead, a 3D style game generated the best FID. And here they also reported their main assignment as we mentioned. So why they say there is best? Because it is most closely to the real image case. And the NSE and the NND, I'm confused here because in terms of to use NND, there should be a kernel function, but they didn't mention what NND means. You have an image and mapping this image to high resolution space, but they didn't mention what kernel functions they use. And in terms of NSE, I am also confused because if we want to measure the NSE, usually we need a ground truth image. So what is the ground truth image they use? They didn't mention it in the paper. Okay. So they try another dataset called the Bratista dataset. And okay, well, the difference of this dataset is there are multiple tumor types. There are 3 tumor types. So again, they use the same module, just increase the number of channels and train their algorithms on a A100 machine for 5 days, and this is the result. However, they only show here no more data available. Okay, no numerical comparison. They just say, yeah, they can do it, but how to measure it? This is another following research question. Right? Okay, so that's all of our slides today.